Okay. All right. Okay. All right. Number one. So number one was where we were dealing with a linear function, and we were placing it in with some. We were placing in it some absolute value bars, and we were also taking the absolute value bars of x, absolute value of x, and plugging into x. So, what on this first one? Are there any questions about what the graph should look like? Where will h and p equal one another? Describing the relationship between the two graphs. That piece is a bit ambiguous. I'll leave it up to you to give a good description. It may be a little bit different than the person next to you. It might be a little bit different than mine. But if it logically makes sense, great. So are there any questions with this first one? And there is some on the back as well. It's plugging in. It's like doing the opposite graph.
What does B asking? What is B asking?
B? It's just asking what does, when I take P, which is the linear function, which is, I'll write it down. So P is 1/2 x minus 3, and A is the absolute value. It's asking, what does it look like algebraically? So it would just be taking the P, which is 1/2 x minus 3, and plugging it into A of x. So what would this be? Anyone? When I take this linear function, I plug it into the absolute value of x.
The absolute value of
Yep. So when it's talking about that algebraic representation, it just means, what's the function look like algebraically? Yep. So then, in F, it'd be the opposite. It'd be 1/2 absolute value of x minus 3. Because it's changing, it's just changing which function you're plugging into the other. And here's one thing that we can start recognizing now. We can see that this is a transformation of the absolute value function. It's a vertical dilation of 1/2 and a vertical translation of -3. So like we can start seeing that now as well as we work through different types of functions. Okay. Are there any other questions on number one? How about number two? Number two was the quadratic. Okay. So this graph is similar to the one that we did in the set of notes, though it is a little bit different. So this one has a y-intercept at 3, -3. It has a minimum at 1, -4, and then a point at 2, -3, and then that's 1. Then the next point I think is at 3, -1. No, sorry, 3, 0. So that means negative 1, 0. And we can see that from the factoring. So this would be Q. And then when I put Q into A, to make M, so I'm taking this quadratic and I'm plugging into the absolute value function, it looks like this. Looks like that. Okay, because what this algebraic representation is x squared minus 2x minus 3. So that means I'm taking all the y values and making them positive. Okay. And then with this one, where are the values equal? When you give the explanation, in my mind, it's where the graphs overlap. Right? But here, it does have two answers. It is for all those values from negative infinity to negative 1, and then from 3 to infinity. Okay? Because I'm going from negative 1 to the left, and I'm going from 3 to the right. Okay? If you had chosen to write this as an inequality, it would have looked like this. It would have looked like that. Okay? Are there any other questions with number 2? The other graph is a reflection over the y-axis. Okay. Because what you're doing is you're taking those y values, you're taking those x values, making them positive, and then evaluating the function. So it looks, if I did like it in red, it would look, I'm going to zoom in too. And the way that I did this is kind of, you could use a table. It looked like this. It's kind of interesting looking. It's kind of a W shaped. Looks kind of like that. So where these points are the same, it's from 0 to infinity. Again, it's because where the graphs overlap. How fancy that? I did a very fancy key. But we can still talk about this. So like for this one, describe in words the relationship between the graphs of Q and N. So Q was the blue, N is the red. It is a reflection over the y-axis. Where and it's almost like the values from 0 to 2 are repeated like on the other side. So, and that is to some degree also true over, to some degree that's also true on the linear function as well. So. Now number 3, when you're describing what each piece is dealing with, you're basically synthesizing the things that you've already seen in the earlier problems. So like for part A, consider a general function and the absolute value function. For what values of x will the original function and its composition be equal? Well, this is representing what happens, like when we look at the quadratic, with the green and the blue. So like, what is going to be true is when each function has positive values. That's even true of the linear function. The linear function, the composition, and the original function only equal when they both have positive values, because that's what an absolute value function does, right? It takes all the values and makes them positive. That's why the shape looks like a V in number 1. Okay, and then for B, it's like kind of like the opposite. I can share with you. All right. Here. So like here is kind of what they say. In general, f composite A of x is when you take the absolute value function and you plug it into the function. This means that the composite function equals f when the input of f is non-negative. One method for finding such values is analyzing the graphs. The two graphs will be the same for values of x that are 0 or positive. And that is what we saw. That is what we generally saw when we compared the green, which is what we started with, and then the red. It's considering all the non-negative input values. So like starting at 0 and going up. Okay. If you saw something different, that is okay. This is a bit subjective because we are in the background still thinking about what are we noticing when we look at functions, and like what are we wondering, right? When it's oftentimes when you ask questions, it leads to more questions, but then also like conclusions as well. So that's even like one method of how you can preach from the Bible. It's like, oh, what questions I have about the text, and can reveal like particular things and something like that. So, okay. Are there any other questions like this one?
What would be the function for B? I'm just having trouble like
this one?
visualizing it. No, for like number 3.
What would be the? It's just giving a generic function. It could be linear, it could be quadratic, it could be exponential, it could be any type of function. That's why it says consider a general function. So it literally could be anything. Even if so take a look, for example, this function. It's a function you don't know how to graph yet. but we will learn. So we see it goes up, down, up, down. When we plug the absolute value of x in, and we try and see where are the values equal, it is for all those values that are non-negative. So going from 0 forward. Even if we check this out. Even if I did something like a phase shift. Sorry, horizontal translation. Carry away, that's all. Plus 4, it's the same. Times -2, it's the same. Oh, horizontal dilation, the same. Oh, how interesting. The graph is just the same for that one. Huh. Didn't plan on that. So that function f, it really could be, it could be any function. Because one thing that we want to start seeing is how some of these concepts, when we think about it in specific scenarios, if we can prove it in specific scenarios, we can prove it in a general case as well. So, all right. Are there any other questions on this one? No. Check our time. It is 10:13. So we have 17 minutes. All right.
For part A, I can't really figure out what it's asking again, but
so what it's asking is, take for instance the quadratic function. I think the quadratic function it's easier to kind of explain this a little bit more. So with our quadratic function, it was x squared minus 2x minus 3, right? So what this is saying is if I took this f and I plugged it into a of x, it's saying where does x squared minus 2x minus 3, since that's my f, where is it equivalent to the absolute value of x squared minus 2x minus 3? That's what it's asking. So then that's why, we go back to number 1, we go back to number 2, and we try and look at what is similar with those graphs. What is that characteristic? Now I know we didn't graph in number 1, but it follows the same principle that we saw in number 2. So let me go back to that one. So here, we started with the green, and that first composition gave us 2. And so what this is, so when it says, explain how you determine an answer, we are seeing where the graphs are overlapping, but even maybe more specifically, we're looking at where the output values are positive for both Q and for this one was M. So we're seeing where are those output values positive. When we did the other one, it was where did it share the same input values that were the same. So yeah. Are there any questions? Are there any other questions or comments or thoughts? Okay. What I will say is that when we think about what the absolute value bars do, and when we look at the graphs, when we take the f, like this function, and we plug it into the absolute value, it kind of lines up in that explaining our reasoning should be talking about those output values. Because what we're doing with this one is that we've taken the output values and we've made them all positive. Whereas with part B, this is talking about taking the input values and making them positive and plugging them in to the function. So then our justification would have to be talking about the input values. When we look at different characteristics in math, it becomes really important that we are paying attention to just different types of patterns. I know sometimes it's a little bit harder to see, but it is when it's harder to see that we're going to be stretched as students to see some of these threads that will work with like linear functions, quadratic functions, and even like other types of functions you don't even know about yet. So, like here's another example. I changed this to I don't want them to be the same color. So. So it's like this is a type of function that we've not talked about yet. We'll talk about it in Unit 3. But this same idea of I'm taking the absolute value of the output values is taking all those negative values and making them positive. Where the values are equal is where both functions have positive values. So that's why it's starting at 1. At 1. And then going forward. That other graph was interesting because it was like f of absolute value of x. It's sending part of the graph the opposite direction, which we'll learn that you can't, with this original function up here, you actually can't plug in a negative value. We'll talk about that later, but so we are trying to build our repertoire of like, as we look at functions, what are the patterns that we are noticing? So we are still trying to know, we're not just trying to look at things black and white, we're trying to look at these concepts that can be applied in different types of scenarios. So, okay. All right, so if you have your name on your paper, I will collect this one, okay? We have 10 minutes. I'm just going to give you time to work, okay? Yeah, I'm just going to give you 10 minutes to work together since there's no like career time today for you guys to be able to work. Yeah, does that sound good? And then we'll just do questions tomorrow. And then probably no homework over the weekend. Cool, awesome.